Okay, so chapter 10, bonding and properties of solids and liquids, Lewis structures of molecules and polyatomic ions. You're going to learn what those are. Resonance structures, shapes of molecules, electronegativity and bond polarity, polarity of molecules, interaction forces and changes of state. I want to tell you already right away what the concept of resonance structures are. It's a way of drawing the same molecule with the electrons in a different position. That's it. It's the same molecule, but the electrons are in a different position. Okay? Why do we do that? Because electrons aren't really where you see them. That's the best pictures we can draw. Follow? Okay. So I want to make sure I tell you that to hang on to that particular thought. So here we go. We'll get through this. A Lewis symbol. A Lewis symbol is a convenient way to represent the valence electrons. We've already gone through our work session talking about what valence electrons are. That's what you've already done. You now know how to draw them, right? You can draw valence electrons. Lewis symbols of selective elements are given here. We're showing you some examples of these Lewis structures. These are the ones you've already done in our work session. You know how to do them now. You know how to look at the periodic table, count across. You know how to write out the electronic configuration. Now simply draw the dots. Don't let drawing the dots fool you or scare you. Draw the dots. Here, what happens in a Lewis structure, we have hydrogen. If you look on the periodic table, it's 1s1, right? That means it wants to bond conveniently one time. So if you take two hydrogens, they come together. Here, voila, we get this hydrogen molecule. So here they are simply going to share these two electrons. Okay? And that's what happens. So we go from something that has high energy to something that has lower energy. This is something we can put in a tank. This is something that's blown up the tank. So the molecules are represented by the Lewis structure. Now there's this rule that's called the Octet rule. Okay, meaning that when elements and compounds will like to have 8 electrons shared around it. Now, that is not true for all elements and compounds on the periodic table. But the reason the rule exists that way, which with its flaws, is because the last row 18 in the periodic table, all have 8. They're noble gases. They're very satisfied doing nothing. They're satisfied simply being a gas, okay, and not interacting, okay? And so the other elements and compounds will like to do the same thing. But they never exactly reach the same nobility as those, but they seek to do that by putting 8 electrons around it. You're going to learn that it's not simply 8 electrons, but it's sufficient electron to satisfy its valence electron structure. Once that's satisfied, it's happy. You get it? That's what you've been doing already. All right, so here it shows you it only has 2, and there's other exceptions to this rule as well. We'll show you those. Here's an example. If you draw the electronic configuration, the valence electrons of fluorine, it comes together. Fluorine's diatomic in its natural state. Does everyone see how this is working now, based on what we showed you earlier? This is what we already showed you. Does everyone understand where we get these 7 dots from? These are the valence electrons. You look on the periodic table, and what's its highest energy level, the number of electrons there. And this is going to be a combination of S2 and P5. Take it, yeah. Here we told you this information in earlier lectures about the diatomics. You'll want to memorize these and know that these are the diatomics. Okay? Their valence electrons are more comfortable when they are as a dimer than as an individual. Here, we show you some other Lewis structures. What do we know about carbon? Remember carbon early in the work session? We said it'd like to bond how many times? 4 times. Look, 1, 2, 3, 4. That's why methane's stable as methane, because carbon likes to have 4, so it's 1, 2, 3, 4. Nitrogen, if you do the nitrogen has 5 valence electrons. If you draw them in the circle as we draw it, you'll see that there are 3 convenient dots available for bonding. So we have 1, 2, 3. If you draw oxygen has Oxygen has 6 valence electrons. 1, 2, 3, 4, 5, 6. Has 2 convenient places. Hydrogen has 1. Therefore, we put 1 hydrogen, and we get H2O. Okay? That's how we get those. And that's what we just showed you in the work session. Here, so, multiple bonds. We can have single bonds and we can have double bonds. And we do that to accommodate the valence structures. In general, in this class, so make a note of this, these will be the ones. The ones where we will look for multiple bonds, we limit the scope here to basic chemistry. Ozone, oxygen, carbon monoxide, carbon dioxide. Practice Lewis structures of those. Don't just look them up to memorize them, practice them, yes.
Can you repeat that one more time?
Yes, I can. Ozone, oxygen, carbon dioxide, carbon monoxide, and did I say another one?
Oxygen, carbon dioxide, carbon dioxide.
Okay. That's it. The other one that occasionally shows up, you can just write on your list of nitrogen itself, N2. Occasionally put it on there. So these will be the ones. Why nitrogen? Because it has a triple bond. Okay. So we draw them. We'll practice these. So here, now, chemists have a funny way of drawing these. Each line represents 2 dots. So occasionally we like to draw the center atom where we draw the lines, and then we draw the rest of these. The total dots have to add up to the total valence electrons of all the elements. You get it? So for example, boron, which is in 13, has 3 valence electrons. Chlorine in 18 has 7 valence electrons. So we have 3 chlorines, so 3 times 7 gives us 21. 21 plus 3. So if we count all of these, we'll have 21 plus 3, 24 electrons total in there. And to count them, we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24 electrons. Does everyone see what I just did? No? Kind of? We're good? All right. Resonance structures means I'm going to take these electrons and I'm going to move them to different locations. The resonance structure that I will look for from you, that I certainly expect you to know how to draw, is ozone. Any others, I will tell you in advance. I will tell you which ones. In your homework, you'll have to do whichever ones the homework asks for. On the exams, know how to draw ozone, because it will be on there. It will absolutely be on there. Okay? All right? So you'll want to play with ozone. There it is. My favorite. Ozone, we know the purpose of ozone, right? To protect us from what? UV radiation. Which UV radiation does it completely block out? UVC. Which ones does it let through? Which one it lets through all the way in? You guys got it down already. You follow? This is what we've been introducing to you. And by now you've kind of gathered I like to do it like that. The last lecture is usually something, and we've tried to introduce the concepts. Here it is, resonance structures. We're showing you that you can draw ozone in its final resonance structure. Let's see, the electron dot for ozone is this, 18 valence electron. Why 18? It's 3 oxygen, right? 1 oxygen has how many valence electrons? Is on the board? 6, right? So if you have 3 oxygen, that's 3 times 6 is 18 valence electrons. So I have to put these 18 valence electrons where it doesn't violate the rules of science and physics, more or less, more than anything else, that says it can only accommodate 8 electrons around each of its areas. Okay? So I draw these, and we'll practice this next week. I don't know if you practice these in the lab or not today. We'll practice these, but we have ozone. So we have 1, 2, 3, all these oxygen together, and so we can draw them like this, or we can draw them like this. Does everyone see it? What a resonance structure is? The double bond can be over here, or it can be over here. This basically means the electrons are doing this, by the way. They're not here, they're not here, they're back, they're doing this. That's why we draw resonance structures. You've seen a benzene ring that you'll learn way later near the end of the semester, last week 11, where you draw benzene with a circle in the middle. The reason you draw benzene with a circle in the middle is because the electrons are not in one place. Yes?
I have just a question about
Sure.
that. So, because I've been working on it because I read the chapter a couple days ago and I can't figure it out. So I can't figure, so the ones that are circled and they're trying to move, so oxygen only has 6 valence electrons. And each one's, of the ones like on the sides, have 6, but they
Yep.
also have the bond. So I must be missing.
The bond is 2 electrons.
Correct. So
See this as see this as
2 more.
as
Right.
dot dot. Don't see it as a line. Does everyone follow? When you start to count, you want to see this as dot dot. In some of my freshman classes, I won't let them draw the lines because it always throws them off.
Well, the middle
Yeah.
oxygen molecule, did the other one like steal it, and that's why they...
That's right. That's exactly what happens.
Okay.
These will, that's a good way of looking at it. It will absolutely steal whatever it takes to get it to balance out.
Okay.
Because the electrons are never sitting in one location. They're moving until they find a comfortable place. That's exactly what's happening. That's what happens with sodium chloride. The reason it's a salt. As soon as sodium goes with chlorine, and remember sodium has that 1 electron, chlorine has 7. It said, the heck with it, I'm sucking them this way. It steals them. Did that help?
I think so.
So-
I'm going to keep working on it.
Yeah, just keep working on it. But I'm going to draw out just a start right here, just to show you. Okay?
Yeah. Yeah, I think I'm just, even getting to that point, I think I'm kind of,
Okay, to get to this point,
right, because I got that they all have 6,
then you just,
and then they all,
they all want to bond how many times? 2 times.
2 times.
You watch for that too, you get it?
Right.
Right? And so you're just going to push stuff around until it works. Okay, you're going to make me tell this to you, and I'm going to have to cut this out of the lecture on this audio, but here's how you do it. It's like Legos. You simply keep connecting them until they work.
Okay.
There's no magic to it except that. But I can't tell you that. You just simply keep connecting the dots until they work. And I'm going to show you. And everybody has a mental way of doing it differently. Okay? But I'm going to show you, okay, I'm going to do it this way for now. To start. So the first thing I do is, I know I have 3, so I just got to use a little bit of, common sense of I'm going to put that first.
Okay, so I think I answered my next question then. So the reason that there
Two,
isn't
four,
a
6.
double bond on each side is that that would give 10 to oxygen in the middle.
That would give 8 to oxygen in the middle.
Because if there's a double bond,
Here, there, they're going to move it here, right? 2, 4,
Right.
6, 8.
right, it already has 8. So
It only has 6.
6 there. So if they give the double bond on one side, it has the 8 in the
It
middle.
has 8 in the middle.
So the reason there isn't a double bond on both sides of it is because that'd be too many for the middle oxygen.
That is correct.
Okay. Okay, I feel
That
like
is
I'm getting
absolutely correct.
Okay.
You push the Legos until they work.
Yeah. Okay.
You get it? That's absolutely why. It sounds too simple, doesn't it? But these electrons do that naturally. It's just we have to find a way of force drawing it so we can communicate the signs. Lewis structures are force drawing of electrons. It is the oldest system of drawing them, right? And many scientists today don't like using it because they prefer to just use the model on the computer. And I suspect at some point this will be put in textbooks as a historical note. Okay? But until that happens, we still teach it. But that's exactly what happens.
Okay. I think it's starting to click now.
Yeah.
I did Lewis structures in high school, but it's all coming back, I think.
Yeah. But you're basically forcing the Legos, you're moving things around, you're moving the dots until they work. And so if you look here, we have a dot over here that needs to be satisfied, a dot over here that needs to be satisfied. So we've got to really just pick them up and move them around until they fit. You get it? But we won't violate the rule of having more than 8. And I will tell you that for things that involve carbon, involve 14 through here, okay? They will fit the octet rule of 8. Group 13 back won't always put 8 around. So, but when you get it, and you'll learn those. Did that help a little bit?
Yes.
Okay.
Yep.
But what you're thinking is exactly what's happening. It just seems so weird that that's what it's doing.
It does.
Yeah. But once these electrons, what happens is you take the electrons, so what you break to have is 3 inside of a balloon or something. You have an oxygen, and they all have electrons. And they're saying, let's share these electrons and trade electrons until we're all perfectly balanced. Because without that, they're high energy, and they want to be lower energy. And that's what they're seeking to do. Okay? We'll work through some more next week as well. And this is what it looks like when it's carbon. This is another one here. Carbon dioxide, same thing. How many dots does carbon like to have around it? 4, right? You see this 1, 2, 3, 4. Does everyone see that? Each line, right? 1, 2, 3, 4. And 1, 2, 3, 4, 5, 6, 7, 8. So that fine. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8 is really happy. Okay? And this happened to be linear for that reason. Here we show you the different shapes. Notice here, these linear molecules are here. This trigonal group here, oh, that's not exact. This is called a trigonal group here. It's called trigonal planar. These are the shapes of these. Okay. Note that when you're trying to draw your Lewis structures, make a note. Group 13, the central atom is the central atom on group 13. If the central atom is from group 13, it would typically only have 6 electrons around it, particularly for the compounds that I'm going to give you. I'm limiting the scope of what you're going to see. Okay? And by the way I limit the scope is based on the fact you're nursing majors. I look at the material that you're going to be seeing in nursing, and you're not going to see some of the other exotics. I'll tell you which exotics you'll see. Okay. These here, jury's out on whether I'm going to get you to memorize all of these or not. I would start to look at it though. Electronegativity, here's something for you to note. If 2 elements bonded together are different, it creates a polar bond. It is that straightforward. If 2 elements bonded together are different, it creates a polar bond. Do not second guess that rule. It's always the case. So, if I draw oxygen, O2, are these elements the same or different? So there's no polar bond. Got it? No polar bond. Keep that in mind. Same molecule. Bond. Okay? Next question. Are these 2 elements the same or different? So there is a what? Polar bond. Everyone follow? You must have a polar bond first before you can have a polar molecule. Okay? What about this? Any polar bonds?
No.
See how quickly you get that? You simply look at polar bonds.
Yes.
Okay. And water happens to be polar bonds and a polar molecule. Follow? CCl4. Any polar bonds in this molecule? Simply being different makes it polar. But it turns out, yes, polar bond, but carbon tetrachloride is not a polar molecule because it has pull in all 4 directions, cancels it out. When it has even pull, it cancels out. Non-polar molecule with polar bonds. Electronegativity simply says that the direction of the polarity is going to be towards the right side of the periodic table. things on the right side of the periodic table are going to pull on electrons more. Does everyone follow that? Okay. Which means in the case of water, H2O, that looks like this. Water pulls on electrons. This little symbol is called a dipole. This is how we represent a dipole. Oxygen is pulling electrons. That's what makes it polar. And it has an overall dipole in that direction. So the most electron-negative elements are on which side of the periodic table? Right or left?
Right.
Right. Get it? So everyone follow that. You know that now, right? The P's have more electrons than the S. How many electrons can accommodate total in a P? Now you get why. Okay, just from the periodic table. Okay, if it has more electrons, it's more electronegative. All right? So in the periodic table, fluorine is the most electronegative on the periodic table. We will not be worrying about the values, but electronegativity does have assigned values to it. What we will be concerned in this class is the trend. Okay? The trend for electronegativity moves from left to right. Oddly enough, from bottom diagonal to this direction here. So your most electronegative species are here. Okay? All right? So fluorine is the most electronegative. Here we show you here on this trend table, electronegativity increases in that direction, decreases here, which means increase. So we go up and across, but really it's like this. So sodium is more electronegative than potassium. Fluorine is more electronegative than lithium. These are trends you have to simply memorize. Bonding, polarity of bonds. We just showed you that. How do you know polar bond? Different. And the polarity is going to move toward what? The most electronegative species. So if I have sodium chloride, which is most electronegative, sodium or chloride? Chloride, very good. So which way does the dipole go, the electrons go? Get it? Does everyone follow that? In fact, chloride is so polar that it's called ionic. Okay? That's how polar it is. And ionic is completely ionized. Okay? Here, showing you how it shares electrons here, shares electrons here. Chlorine is more electronegative than hydrogen, therefore, notice the partial negative. We draw partial negative to indicate the direction of the dipole. So the dipole is in this direction. Okay? Does everyone see that? We're good? Yeah, hang in there. No, it gets tough. Here, these are nonpolar bonds, are they not? Right? And if it's nonpolar bonds, nonpolar molecule. Are these polar or nonpolar? Nonpolar. So nonpolar molecule. What about the bonds in this, polar or nonpolar? Polar. Right. They're only mildly polar, but they're still polar. You get it? Which direction do they move? Toward the carbon or toward the hydrogen electrons? Toward the carbon. So you got what? N toward carbon, N toward carbon, N toward carbon, N toward carbon. All four N toward carbon. Do you think that makes it polar or nonpolar? Nonpolar. Why? Yeah, they all cancel out. It is that straightforward. We're not going to be doing the calculations. What we expect you to know is the trends, like we just went through. And here we show you. Carbon tet. I did that one earlier. Here we show you here. This cancels, that cancels. You get it? Oxygen more electronegative. Cancel, cancel. We told you this one earlier. Right? HCl. Polar bond and polar molecule. Polar bond and polar molecule. Let's look at this one. Polar bond and what? Polar molecule. These are the examples that we've already gone through. Now, this is kind of a fun one, isn't it, right? What did we tell you? Fluorine's the most electronegative thing on the periodic table. So we're going to get a pull toward fluorine. We have 1, 2 polar bonds, right? And a completely polar molecule. There you go, folks. You survived chapter 10.